Well, I need,
Okay, here we go. Hey, nice job on the homework. I will do that pretty much every day where I'll walk up and ask if you finished it. I put full trust in you. Like, you don't have to show me. Once in a while I will give extra credit for proper notation, and I'll kind of warn you about that, or maybe I won't warn you, but anyway, once in a while I will look just to see if you're writing in a way that's going to get you points on the written section of the test. But I'm not asking you to prove to me that you have it done. I take your word for it. So, but nice job on the homework. There were only a couple people who didn't get it finished. That happens to everyone. Like, really, if I have a whole class and there's just a couple who, whatever happened, it just didn't get done, I don't really stress about it. Just don't let it pile up. I don't remember if I told you in this class, but I did have a student one year. It was about February. She was a very high-performing student. She was a junior in AP Calculus. I think her ACT score cumulative was like 33. Okay, so very high-performing student. But she got a little bit behind, and then suddenly she just like wasn't doing anything. And she failed that term, and I talked to her later, and she's like, yeah, once I was 2 weeks behind, it just felt impossible to catch up. Like, it's just not the kind of class that you can dig out of quickly. So anyway, just don't fall behind. So, okay, we're on to the next packet, some pink. Moving on. All right. So we'll just work on number one here. It says use limits to show whether or not the function has a left half horizontal asymptote. Some new words there. You've heard them in previous classes. Probably not the thing left half. That's my invention, because I felt like students were getting a little confused. In this class, you will encounter AP problems where a given function will have a certain horizontal asymptote on the right half of the xy plane, but a different horizontal asymptote on the left half of the xy plane. And they don't distinguish. They just ask if there's an asymptote. And it's kind of a trick question, because sometimes you have to notice that there's two of them, and they don't give you any hint that the left and right are different. So in this packet, as we start talking about horizontal asymptotes, I thought it would help you to just kind of implant that in your memory if I refer to them as left and right half. Questions about that? Okay, cool. It says use limits to show. The reason they say use limits is because horizontal asymptote and a limit as x approaches infinity are exactly the same thing. So in a previous class, I believe they used the word end behavior, not if that's familiar. Okay. They won't use that in AP Calculus. They'll just ask, is there a horizontal asymptote? Sorry, oh, you're good.
can I just take 15 seconds with your class?
Take 20 or 30.
Oh, that's so nice. Hey guys, just wanted to come in. I apologize for the interruption and introduce myself. I'm Mr. Dixon. I'm one of the assistant principals here at the school. New to Lone Peak High School. Happy to be here. Anyway, and just to let you know too, I'm over the letters A through C, so last name A, B, or C. I'm your administrator, so if you need any help with anything, or if you just want to chat, or if you're like, you know what, I need a treat, you can always come to my office, right? Anyway, but I hope you have a happy Thursday. I'm happy to be here. I hope you guys are happy to be here too. I love being here at Lone Peak. That's all I got.
Perfect.
Have a great day, guys.
All right, thank you. Okay, so key thing, they won't use the word end behavior, they won't use left or right, they won't even say limit, they'll just say horizontal asymptote. And what you have to do is say, oh, I'm supposed to be thinking of horizontal asymptote, then I must write down the following. So go ahead and write this on your pink paper. We're going to find the limit as x approaches. Now, new this time, different than we've done. Because we're looking for a left-hand horizontal asymptote, left half, that means we need to think of x values that grow forever negatively. So we are going to specify that x is approaching negative infinity. like that. So this is also different than what we've done on the buff packet in that there is no left or right hand limit. It's a similar but different idea. X is going to become negative forever. It doesn't approach a certain value, it just goes negative forever. We are finding the limit of this function f, so we've still got to put, like we did on the buff packet, an f of x here. That's how you begin. So they will not give you any hints about that. They're not going to give you any hint that that's what you're supposed to do. Like they won't say use limits. They'll just say, does this function have a horizontal asymptote? You have to remember, oh, that means I've got to go find the limit. We're going to go Ellie, then Zach. Go ahead.
Is there a reason why you put a space that big, or did it?
Right here?
Yeah.
No special reason. I'm not really sure why I did it.
Okay, I just was wondering if we were going to write something.
No, my apologies. Nothing goes there. I don't know why I just left it so wide and 3 points for Ellie. Zach? Oh, keep asking. Like my number one priority is like, you just got to get you guys talking. So no, keep asking, please.
So you said as we're going to one, are we going to want to put a minus or a plus, like we've normally been doing in the top right of the infinity?
Gotcha. When you're dealing with x approaching either positive or negative infinity, there will never be a little plus or a minus because it's a related but different idea. When we had x approaching 5, well, we could think of the x value as being slightly more than 5 or slightly less. But if x is approaching infinity, there's no such comparison. X is just going to grow forever, either positively or negatively. So no, there will be no plus or minus here. No left-hand limit, no right-hand limit, just x approaching negative infinity. 3 for Zach. Cool. That's where you begin. I'm giving you hints on this homework packet because it's the first time that that's how you begin, but they won't give you any hints. They'll just say, in fact, they don't even often say horizontal asymptote. They just ask if there's an asymptote, okay? You have to figure out the rest. Questions? Yeah, please.
How would you figure out if it's like a horizontal or a vertical asymptote?
Gotcha. Pondering that one for a second. That part I may have misspoken there. They probably will specify that, whether you're looking for vertical or horizontal, but I'll have to double check my notes. I'm not positive on that one. 2 for Hannah. Anybody else? Please.
So normally we would find the left and right half if like further down the line, but in these we're only finding the left half.
That's well said. 3 points. What I have seen on AP tests, and I've maybe said this before, I spent a lot of time really studying old AP problems, trying to get a firm idea as best I can what kind of things they might ask you. So I went all the way back to like 1969. That was when they first started making, maybe that was the first year they actually gave the test, I don't know the history. But that was the first year they made questions public. And I've studied every question that has been made public since then. Okay, hundreds of questions. And they, almost, I'd say 95% of the time, it's a right half horizontal asymptote that they're really testing you on. So I normally start with x approaching positive infinity to see if that's enough to kind of answer what they're asking. And then I go to negative if I need to. For the packet, I'm going to have you do both just for practice.
Yeah.
Did that kind of clarify?
Yeah, that makes
Okay.
sense.
Part of what I'm struggling to answer, Clark, is this. Most of the horizontal asymptote questions have actually been multiple choice. But if we practice in this kind of more open, big idea way, then you're well prepared for them.
Yeah.
So, okay. Anybody else? Awesome. Okay. Brand new flashcard here today. This box right here. I have found, okay, how do I say this? We could study limits to a much greater depth than we will study them. We're going to study them to a depth that will allow you to get a 5 on the AP test, but you could go a lot further. But for the purposes of our class, this little sequence of thoughts has never failed me. If I simply follow this sequence of thoughts, I've been able to answer every limit question that has ever been posed, at least made public, since 1969. The first thing you're going to do, step one, is you're going to identify whether x is approaching positive or negative infinity. So I put a positive infinity, but it could also be negative. The rule is the same. If that's the case, you're going to do what I call, you're going to compare terms that add. I'll explain what that means in a second. So that's the very first thing you do every time you encounter a limit problem, is you ask yourself, is the limit, is it where I have x approaching positive or negative infinity? If yes, we're going to compare terms that add. Number two, if we can, we'll factor and divide. And the only reason we're factoring is because we're looking for a factor in the numerator that matches a factor in the denominator. This little note here. Otherwise, there's no real reason to factor and divide, because we wouldn't be able to divide it. So. Step three, we've already practiced this one. So we've not practiced step one or step two yet. We've not had to practice those in the buff packet. In the pink packet, we'll introduce that idea. We have practiced three, checking the left and right hand limits. That doesn't apply if x is approaching infinity again. That only applies if x is approaching a finite value. So, questions? And then the very last thing, I'm going to have you put this on a flashcard and memorize it, but you won't use this for some time. There's a fourth method that's known as L'Hopital's rule, named after a French mathematician. We won't practice that for a while, but you need to get that in your head that eventually that will become an option. So it's just not an option yet.
It does.
Questions? Okay, cool. Here we go. So that's my thinking. So I have to find the limit of f. So step one says x is approaching infinity. Yes, x is approaching negative infinity. I want to compare terms that add. There's a sign on the wall. The student's name was Amanda Lindstrom. She was kind enough to make that sign for me. She made the sign because it made a huge difference for her. Like, she was really struggling with limits and actually a lot of other concepts until it just suddenly clicked one day that whenever I was talking about terms, I was just saying it was a thing plus a thing plus a thing in her language. Okay? Versus when I was talking about factors, it was a thing times a thing times a thing. And as we talk about expressions throughout the year, you'll see me go back and forth like regularly. And it's usually just a matter of perception, like how you look at something, whether you say you are looking at terms or looking at factors. For example, if I look at this numerator here as a whole, raise your hand please, don't say it out loud. Would you think it is best to say that you are looking at a thing plus a thing plus a thing, or are you looking at a thing times a thing times a thing? Use really strong mathematical language. Hands up. What would be your vote? What do we see? Terms or factors? Let's go, Grace.
Terms.
So Grace votes terms. Who votes with Grace? Point two for Grace. So here we go. X is approaching infinity, negative. We want to compare terms that are added. So all that means is we're going to look at, actually do this for me. As you look at the numerator, do you see one term, two terms, three terms, four terms? Show me. How many terms do you see in the numerator? Just use your fingers to show me. 1, 2, 3, 4, 5. How many? If you're doing this, give yourself 3 points. Cool. There are 3 terms in the numerator. We need to compare them. So what we mean by compare is we have a negative 12, we have a positive 7x, and we have a negative x squared. Notice how I kept the sign with each value, because I am comparing terms that are adding. So I think of these 3 terms as being added together, that's what they're doing, and I simply have to think about, hey, as x gets really, 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 really negative, and those 3 things add, if you did this on a computer, you would find out that little by little, this doesn't make any difference, and this makes very little difference either. the final result is 99.9999999% dependent on that single term. The other two terms are adding something, but they add so little it really doesn't make any difference.
Is that 99.9999 going infinitesimal?
It is. Yeah, the more the x becomes negative, the more that this term dominates. When you add the other two items to it, it doesn't really make much difference. Here's kind of an example of that. 2 points for Caleb Hughes. Yes? Okay. I'm just making sure I remember your name. So here's a spreadsheet showing that idea. I'm taking a value, so like just n plus 3n cubed minus 5n, and I'm making n get more and more negative. So it shows n becoming very, very negative. It shows what happens when you take 3n cubed, how large that becomes, compared to 5n. When you put them together, the spreadsheet couldn't even show the contribution from the negative 5n. So I've noticed this number looks to be exactly the same as that number. They are different, but the computer can't do it. Like the numbers are so different. Please, Ellie.
Is that because that it's like cubed or squared?
It is.
Okay.
Yeah, the power is what's making the difference. 2 points for Ellie. This is 5n to the first power. This is 3n to the third. And it doesn't really take a very large n. That's only negative a billion. We're going to negative infinity. Okay, but at negative a billion, the computer can't do it anymore. As far as the computer knows, it's only working with 3n cubed. It doesn't even see the 5n. So when I say compare terms that add, that's what we're talking about. I'm simply looking at those three terms and saying only the negative x squared even makes any difference. Other questions? Okay, oh yeah, please.
If there are
Liza.
multiple factors with exponents, is it the one with the biggest exponent?
It is 3 points. So as it is Liza. Okay. As Liza said, when you're comparing the terms that add, for the buff packet, all you're ever comparing are what are known as power functions. This is negative 12x to the 0 power. This is 7x to the first power. This is x to the second. It doesn't matter whether it's positive or negative. Whatever power function has the highest exponent, it will dominate when they're adding. Anybody else? Okay, written portion of the test. That's half your points on March 13th. Sorry, May 13th, March, that'd be panic. May 13th. So on your pink sheet, you must write the notation correctly. We will, at some point, I may give you a quiz, and if you don't have perfect notation, you don't get any points. Like if they don't give you partial, it's got to be right. So you've got this written down already. The next line, make sure you have an equal sign. You cannot forget the equal. Cannot forget the equal. It's no different than forgetting a period in an essay. Like it's just a mess if you don't have periods. You have to have the equal to show that, hey, this is the same as this. We're still finding the limit. And I tried to put the solutions in the back of the pink packet to be fairly complete, so you can see what I'm expecting, what the AP graders will expect in terms of notation. So you have a good model to look at. We are no longer going to be finding the limit of f per se. We're going to be finding the limit of just a numerator of negative x squared, because we have logically deduced that the other two terms aren't really making any sort of any meaningful contribution as x becomes extremely negative. Questions about anything? So here's a vote for the whole room. This formula, let's race through this. So make sure you're making sense of this. Now when we compare the terms in the denominator, the only term that really makes a contribution as x approaches infinity is the positive x squared. So we write it like that. Question?
So just -1 then? Or
You've got the right thought. I want to show one more step just to illustrate a pretty important idea, but your thinking is very good, too, for August. Also want to ask a question here. We have a formula up here in blue. We have a formula here now in green. Oops, that was not what I wanted. Green. That's still not green. Change, man. There we go. Okay, this means true. This means false. I need you to vote. It's kind of a trick question, but I'm not trying to trick you. I'm just trying to make a point. True or false? The blue formula is identical to the green formula. True, false. The blue formula is identical to the green formula. True or false? Okay, everyone gets 2 points for voting. We really had a pretty much 50-50 mix. The blue formula is different than the green. Like, they're not the same. However, the value of this limit in yellow, F is the blue formula. F is the blue. If I find the limit of the blue formula, I'm going to get exactly the same result as if I find the limit of this green formula. So even though the blue and the green aren't the same formulas, because I'm finding the limit as x goes to infinity, they are equal. The limits are equal, not the formulas. That will vary from problem to problem in this packet. Sometimes you'll say, oh, the formulas aren't really equal, but the limits are equal. Questions about the difference? Solid. Okay, next one. So now we do, so we've done compare terms that add. We're going to do some factoring now. And I want you to write this for sure. Eventually, if you can do this without writing, I'm okay with that. But for now, write it down just to emphasize the idea. Very important concept here that we're going to use all year long. So your next line is going to say, don't forget the equal sign. Don't forget to write limit as x approaches infinity, negative. Now what we're going to write is we really have a -1 constant in the numerator. We have a +1 constant in the denominator. And that's being multiplied by x squared divided by x squared. Questions, please.
Do you want us to put the equal sign underneath the equation, or do you want to, like, could you put it where it's like lined up horizontally, or do you want it vertically?
Gotcha. 3 points for Ellie. A couple of options as far as where the equal goes. To be fair, I can't say they wouldn't give you credit if you did it in a different way. I don't want you going across the page, though. Like, once in a while, you'll see me go across a little bit, but it really leads to a lot of mistakes. Like, your brain can track your work a lot more effectively, like when you go straight down the page. So I know that's a little bit nitpicky per se, but I really will not give you points on a written test if you're going across. At least for a while, until it causes mistakes. Just learn to go straight down the page. If you want to put the equal on this side instead of this side, like you say, something like this, Ellie, that this limit is equal to that, which is equal to that, they'll accept that style. I prefer the other, but anyway, I don't know if that answered your question. Okay. Anybody else? Awesome. Let's vote again. Let's go orange this time. So, true or false? Word to word. True or false? The green formula is identical to the orange formula. True or false? Show me. The green formula is identical to the orange formula. Did much better on that one. Give yourself 2 more for voting. The correct answer is true. Green is exactly the same as orange. All I did was factor. Blue was different than green because I made this assumption that these terms here didn't make any difference. This term and this term just didn't matter. But that's because we're going to x values that become negatively infinite. So blue is different than green, but green is the same as orange.
So blue's different from green just because of the other factors,
The other terms.
the other terms.
Yeah, no worries.
Okay.
Exactly. Yeah, you can't ignore the other terms if x is like 5. But when x becomes negative a trillion, they don't really make much difference. Here, all we did was factor. We didn't ignore anything. Just wrote it differently. 2 more for Clark. Yeah. Sweet. Okay, so now we're exactly where August led us. Now what your brain should be saying is this. Okay, so warning to everybody look at me. Warning. This is a spot where you can copy what I do, but if you don't understand how I did it, it's going to cause trouble later. You just have to trust me. At this moment, you have to think, okay, the x that I'm plugging in is going to become more and more and more and more negative. But it doesn't matter how negative x becomes. I'm going to take whatever x is, square that value, divide that value by the exact same thing. So this will always equal what value no matter how large x becomes. Just say it. 1. Does that make sense? That's the whole point of writing it out like so. Now you can do it in your head, but at first I want you writing it out just to reinforce it. So no matter how large x becomes, 1 times negative 1 is simply, we can go across here, there's not much left, simply negative 1. Questions? Please, Hannah.
What if it's like x cubed on top and x squared on the bottom?
Gotcha. We'll do an example of that, I think, or maybe not, I don't know. There'll be one in the packet for sure. If that had been the case, I would have ended up with a statement like this. So I'm going to leave everything the same, Hannah, if that's okay, and just make that one subtle difference. Do you want the extra x on the top or bottom? I don't care.
It doesn't matter.
Okay, so we'll just put it on the top for now. Is that okay? You would have ended up with something like this. Does that make sense? So then your logic is nearly identical. You say, well, as x gets bigger, more and more negative, what is this going to equal, Hannah?
1.
That will still equal 1 because you're taking some value squared divided by the same value squared. It's always going to be 1. But this is just going to become very, 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 very negative because x is becoming very, 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 very negative. So extremely negative times negative 1 times 1, this thing's going to become infinitely negative. Oops, positive, my bad. Thank you. Nice catch.
So you're timesing those 3 things together to get infinity?
Let me say it differently. We start with a formula. This formula will calculate any y coordinate for any x we pick. When we do a limit, we're saying the x's we're picking are just sequentially more and more negative. But that's a little hard to compute, so we make this very important comparison. We say, really, we don't need to find the limit of the blue formula. If we find the limit of the green formula, it will be the same result. And the little question you asked was, well, what if this were a 3 instead of a 2? Like, what if this had been 3 instead of 2? Does that make sense? Well, then we end up over here with this situation. So as x approaches infinity, yeah, we're just plugging in the x and seeing what we get. We're just imagining we could plug in a larger and larger negative number, and what would the y coordinate compute to be? And what this is saying is the y coordinate doesn't compute to be a number, it just keeps growing. So as x becomes very, very negative, y becomes very, very, very positive. Because of how the computation works, where, yes, negative 1 times a very, very negative number would be a very, very positive number. Let's hope that's helping. We'll let it sit for a minute, is that okay? 2 more, please. Anybody else? Very good. Okay. So let's erase this. Let's go back. Come on, let's get that back up to work. Come on. I think we're back to where we were. Okay, cool. Yep. Okay, last thing. Now what they expect you to observe is this. If the x-coordinate is becoming increasingly negative, this analysis is telling us the y-coordinate is going to, in the limiting sense, be -1. So that means this function, you would have a conclusion now. You'd say, therefore, f of x has a left half horizontal asymptote and now be sure you don't write x. The horizontal asymptote is specified with y equal, not x. So that's it. Please, Caleb.
So if we come out with the value with this limit equation, does that mean it does have an asymptote? Okay.
As long, yeah, keep going.
How do we know if it doesn't have a horizontal asymptote?
What will happen is what happened with Hannah's question.
It'll just.
You'll become either positive infinity or negative infinity.
Okay.
A rare case that has never happened on the AP test is you'll find that the value isn't actually settling. It's like you pick different x's, and the value just keeps moving. That can happen, but they've never tested you on it. So, please.
So what would we need to have written down for the AP test?
Gotcha. So,
Like what worksheet?
yeah, I got you. I was trying to think of an example I'd seen on an actual AP test where they might say show, like they would probably be even a little more obviously just say show that this function has a horizontal asymptote. And if you wrote this right here, you would get full credit. Yeah, please, two more for.
It's always going to be x approaches negative infinity.
If we're looking for a left-hand horizontal asymptote, we'll always be thinking of that being equivalent to the limit as x approaches negative infinity, right half x approaches positive infinity. Okay, two more for fun. No, please.
This might have already been said, but if the horizontal asymptote is infinity or negative infinity, can you just say it doesn't have a horizontal?
Correct, correct. No, good question. Two more, please.
If there was more than one exponent in the original function, what would you do?
Tell me what you mean. I'll let you-
Like, because there's only a negative x squared on the denominator and x squared, but what if there was like another exponent up there? Like, would you have to factor out
Oh, gotcha.
the starting function to?
It kind of depends, but let me see if I can anticipate what you're saying. Something like that?
Yeah.
Gotcha. We'll do this one together, but it'll answer your question. So, oh, good comment. Two more. Anybody else? Oh, thank you. Just put on that signal. Perfect. Thank you. Okay, cool. Number 2. Stop. Any other questions on number 1 before I stop the recording? So. Oh, please.
So we don't have to find like the approaching limits because it never touches the asymptote anyways.
No, good question. Just got to rethink what you said. If I'm finding a limit as x gets close to, say, 10, there are 2 ways for the x value that I pick to be close to 10. The x value could be slightly less than 10, or the x value could be slightly more than 10. Does that make sense so far? Perfect. So that's why if we're finding a limit for a finite number, we have to do a left-hand limit and a right-hand limit.
Oh, okay.
I'll keep going now because you got me all wound up. Put the quarter in the machine and finish. If you have x approaching negative infinity, that doesn't really mean the same thing.
Right.
It means the x's you're picking are doing this kind of a behavior where they're not getting close to anything. They're just becoming more and more negative. So there is no left half.
Yeah.
Does that
Okay,
help?
that makes
Well done.
sense.
Two more. Please.
Can I get a drink of water?
Absolutely. Good job.
Just hold on. I just don't want to
Uh-huh.
know exact words.
You're good. This one here?
No.
You talked.
It was like
This one's the right.
Oh, I got you, the answer, yeah. Let me pull it out. And in the back of the pink packet, it's pretty close to this. I later, after making the packet and having it copied, I thought, wait a minute, I should add a little bit more to make it more clear to all of you. So the back of your pink should look pretty close to what you see here, but I've got just a little more wording here to make it a little more clear. So, is it pretty close?
It's like the exact same.
Oh, so I executed it, okay.
Yeah, it's the exact same.
I wasn't sure. Okay. I think some of them I added a little bit. Okay. And I do my best. I can't always find the time to do that, but as much as I can, I want you to be clear on what's expected. So, please.
What would this look like on a graph? Would it be like coming up into the horizontal? Like
So, I found some time yesterday to do that. So here's what the graph would look like. I've never seen an AP question where you have to graph anything. So I kind of like that because I never liked graphing.
Yeah.
But it does help to see it to kind of just cement the knowledge.
Right.
So here's a picture of that function.
Okay.
It's doing all kinds of stuff, but all we're studying
The left.
is the left-hand behavior.
Okay.
And I should change my zoom, but it's a little hard with my, well, maybe I can do it here.
So the right hand behavior in this case is the same, but it won't always be.
If you're dealing with a ratio of power functions, they're always the same.
Okay.
Don't know if it's this packet or the next one. We will deal with some functions that are not.
And then you have to solve both of them.
You have to solve both. So we have to watch out for that. Two more.
So when we solve the left hand, it's just the left hand of the x-axis, like.
Right, like and again, left hand is just my wording. It's not on the test, but it's just to help you understand better. It's as you stare at the graph, the left-hand side. Does that help?
Yeah.
Work. Please.
Are there also two vertical asymptotes on that graph?
There are on this graph, vertical asymptote about here-ish, and another here. They just aren't asking us to study it, so we're just ignoring it for now. So, two more for Zach. Cool. Right. Did I answer your question?
Yep.
Perfect. Let's go back to here. We good? Oh, please. Great.
Does it matter the y is approaching on the top or bottom, or is it just approaching negative?
Oh, gotcha. I'll give it 5. No, really, it's a good question. Mark it down. Everybody look at me. Don't miss this. For as far as the AP is concerned, like I've never seen them ever concerned with that. Whether we are getting close to, whether the y values are always a little lower than -1, or whether the y values are a little bit greater than -1. They don't seem to ever ask that, never have, so I'm not really too concerned. I don't really review it. Here's something to watch out for, though. The technical definition of a horizontal asymptote is simply the limit as x approaches infinity. So, unlike things you have previously studied, you can actually have a function that is nothing more than a horizontal line. Something like this. So this is a very boring function. It's not really interesting at all. But technically, that function has a horizontal asymptote. It's the line itself. Like people have this misconception that you can never touch a horizontal asymptote. That is completely false. Like that arises from the fact that the functions you study don't touch their horizontal asymptotes. It doesn't mean you can't touch the horizontal asymptote.
So what does asymptote mean again?
So all asymptote means is this right here. Limit as x approaches infinity.
Okay.
You take any function and you go find the limit as x approaches positive or negative infinity, you're determining whether or not there's an asymptote. The touching part is, like, don't put the touching part into it. That's wrong. Please. So vertical asymptote has the same name, but it's a very different behavior. And where there is a vertical asymptote located, there will not be a value of the function. There will be a missing spot. So there's no connection of the graph. Like, you think of it as not touching the vertical asymptote. But horizontal is different.
So vertical and touching, the horizontal.
Yeah, vertical they don't touch. Horizontal you can touch. You don't have to, but you can.
Oh, so vertical is no touch.
Yeah, vertical is definitely no touch. But horizontal, you can absolutely touch that asymptote.
So a straight line up and down. I guess that would be undefined.
That's the spot where the function is undefined.
Right.
That's why there's a missing point there.
Okay, is that?
Yeah. It's why people get mixed up. And they have had true or false questions on the AP test. I'll show you one later. And that's how they trick people. Like the one that caught everyone's eye was, oh, you can't touch the horizontal asymptote. Everybody marks that as true. That's wrong. Okay. Next one. Cool. Stop the video.